Hello all, I am Irene. Today we are going to discuss about dynamics of rigid bodies, rotation about an axis for rigid bodies, equations of motion of rotating bodies. So our first topic is dynamics of rigid bodies. So what is a rigid body? A rigid body is an object with a fixed shape that does not deform under force. In simple terms, we can say that the relative position of any two particles do not change under the action of forces acting on it. To show that, I have drawn two figures here. If we look at the first figure, let's take this as a rigid body, and there are two positions A and B marked on here, and the same body when any forces when applied, the position A dash and B dash does not changes. And if the body is treated as rigid, the relative position of A dash, B dash and AB are same. So we should keep in mind that a perfectly rigid body does not exist. Let's take this marker as an example. So if we kept it as this, we know that this is the center, approximate center. And if we are applying a force from here and another force from the opposite side, we can see that the center position does not changes. Or if we rotate it like this on its, I can't do that, I don't have that skill, but still if you rotate like that, you can see that the center position does not changes. I hope you have understood the concept. Let's move on to the next topic, rotation about a fixed axis. When a rigid body rotates about a fixed axis, every point on the body follows a circular path around this axis. It means that, as I told you earlier, when we rotate it like this, let's think that this is the axis here, the center axis, and if you rotate it like that, you can see that every point on this marker is follows a circular path around this axis. If we keep this as an axis, if we rotate it like that, we can see that every point follows a circular path around the axis. The axis of rotation can be any line within or outside the body, such as the central axis in a spinning disc or the pivot point in a pendulum. Okay. Now we can discuss about angular quantities. We know many linear quantities, right? So we can discuss about angular versus linear quantities, but before that, let's just try to understand some of the angular quantities. First one is angular displacement. We know linear distance, right? So it is the angular term of distance, which is angular displacement. It is denoted by the symbol theta. It measures the angle through which the body rotates. It is usually measured in radians. Okay, if we are taking this circle and we have drawn a radius here, and this is a reference point, a reference line here, and the angle between these can be taken as angular displacement. Next one is angular velocity. The rate of change of angular displacement, or it is the derivative of angular displacement with respect to time. Greek letter omega is used to denote it, and it is usually measured in rad per second. We know linear velocity, which is v, and it is the angular term of that linear velocity, and we denote it with omega, which is we already have told that it is the derivative of the angular displacement. Next, we have angular acceleration. The rate of change of angular velocity, the derivative of angular velocity with respect to time. We know that we know linear acceleration. What is linear acceleration? It is the rate of change of velocity or linear velocity. And it's just the concept is simple. It is same as that of the linear equations, but in the terms of angular or rotation in terms. I will show a picture which depicts the angular versus linear quantities. As you can see here, distance turns to angle, velocity turns to angular velocity, acceleration turns to angular acceleration, mass turns to moment of inertia. Force changes to torque, momentum changes to angular momentum, kinetic energy turns to rotational kinetic energy. We will deal with it after some time. Just go through this. Let's move on to our next topic, moment of inertia. That's our next topic. As I have just told you, moment of inertia is the angular term of mass. The moment of inertia represents the resistance of a rigid body to the changes in its rotational motion around a specific axis. For a rigid body, the moment of inertia I is given by I is equal to summation of mass into r square, where mi is the mass of each particle, ri is the distance of each particle from the axis of rotation. Consider this a point in the center, and another point is moving in a circular path around it. So we can call this whole system as moment, and the resistance of this body to go in a circular path is called the inertia. So here is an important one. Moment of inertia depends on the axis about which the body rotates and the distribution of mass within the body. So we can make a question here like, name the things moment of inertia depends on, or what does moment of inertia depends on? Let me demonstrate a simple example to get to know moment of inertia better. So this is a scale. I am applying two forces at the end, the two end points here, and as you can see here, it shows a little bending here. And if I turn this into this side and I am applying the pressure here, it's almost impossible to change the position. There is no bending here. This shows the area of moment of inertia. This stiffness is the area of moment of inertia. So inertia is the resistance to the bending. Equations of motion of rotating bodies. So we know that Newton's second law states that the force on an object is equal to its mass times its acceleration. So here we have rotational analog of that law. For a rigid body rotating about a fixed axis, the rotational form of Newton's second law is torque is equal to I alpha. We know that F is equal to mass into A. It is the Newton's second law. So here we have torque instead of force, moment of inertia instead of mass, and angular acceleration instead of acceleration. This equation shows that the angular acceleration is directly proportional to applied torque and inversely proportional to the moment of inertia. Here I have shown you how. Torque is equal to moment of inertia into angular acceleration. Angular acceleration is equal to torque divided by moment of inertia. And where angular acceleration is directly proportional to torque and angular acceleration is inversely proportional to moment of inertia. Next, we can talk about kinetic equations for rotational motion. We have studied linear equations in our earlier classes, and we are taking it on an analogous term here. Analogous to linear motion, rotational motion has kinematic equations for constant angular acceleration. So here are three equations. We know these equations. We are very familiar with these equations. So I can show you the rectilinear equations of this one so that we can compare and study. First, let me show you the analogous equation. Here, theta is equal to theta initial plus omega initial time plus half alpha t square. The second equation is omega is equal to omega initial plus alpha t. Third is omega square is equal to omega initial square plus 2 alpha into theta minus theta initial. This is omega final, okay. So now let's compare the two equations, rectilinear equation and our analogous equation. Here, when we look at this, we have here the linear displacement here, we have linear acceleration here, and linear velocity here. In this equation, our displacement changed to angular displacement, acceleration changed to angular acceleration, velocity turned to omega or angular velocity. Take a look at these two equations. Okay. These equations allow calculation of angular displacement, angular velocity, and angular acceleration over time. Next, we can move on to rotational kinetic energy. The rotational kinetic energy of a rigid body rotating about an axis is given by k rotational is equal to half I omega square. This is the translational equation half mv square. Here we can see that the mass turned to moment of inertia and the velocity turned to angular velocity or omega. This is the energy associated with the rotation of the body, analogous to half mv square for translational motion. Work energy theorem for rotational motion. The work done by a torque in rotating a rigid body is given by W is equal to torque into theta. We know the equation W is equal to force into distance. This leads to the rotational work energy theorem, where the work done by the net torque is equal to the change in rotational kinetic energy. W is equal to change in k rotational. We know that work and kinetic energy is equal and the potential energy is the opposite of the work done, or the negative of the work done, not the opposite, sorry. Conservation of angular momentum. This is very important topic. If no external torque acts on the system, the angular momentum L is conserved. For a rotating rigid body, angular momentum is given by L is equal to I omega. Conservation of angular momentum is crucial in systems like gyroscopes and in phenomena such as precession of spinning objects. We know the equation L is equal to I omega. Okay, this is a simple example to understand the angular momentum, the conservation of angular momentum. We know ballerina dances, right? So they have two steps. One moving in a circular motion by stretching their hands, and other by closing their hands. In here, we know the moment of inertia is large because the area is large here, and the omega, the velocity, is small. That means if we are stretching our hands, the area increases and thus the speed, the velocity decreases. Then if we close our hands, we know that the area decreases, so omega will be large because of this equation. I will provide a video after this. Just watch it as a reference.
We can demonstrate the conservation of angular momentum the same way a figure skater does by going into a tight spin. I'm not a very good skater, so I'll use this turntable and a pair of hammers. I'll hold them out at arm's length so I get a nice large radius, and I'll set myself in a slow spin. I'm spinning around at a constant speed, and then I draw the hammers close to my body, and I spin around very rapidly. As soon as I move them out, I slow down again. And I can repeat this as many times as I want until the friction of the turntable stops me.
Now, let's move on to the last and final topic, applications and examples. So, flywheels. Flywheels are devices that store rotational energy that is used in engines and energy storage system. We all know sewing machine, not the electrical one but the mechanical one. So it have two wheels, one on the top and one on the bottom. So the top wheel is small and the bottom wheel is large. We are applying pressure on the top wheel, but if it with one spin, this wheel turns multiple times. So it gives, if we give the pressure here, the work is done on the lower wheel. The next one is rotational dynamics in astronomy. The principles of rigid body rotation help in understanding the rotation of celestial objects like planets and stars. We all know Earth revolves around the sun, or any planet, the orbits around the sun. So the planets orbit around the sun due to the gravity of the sun. And there also the principle of rigid body rotation is applicable. Next one is gyroscope. Instruments that use the conservation of angular momentum to maintain orientation, which is used in navigation system. I will provide you a video to know better of the gyroscopes.
This is a gyroscope. If we simply stand it up, it will obviously fall due to Earth's gravity. However, when we spin it from the center, it creates angular momentum, which allows any object to remain stable with ease. In this case, it won't be affected by the gravitational force. Even if we change its direction, it will remain stable in its position. This principle is used in our bikes, cars, and aircraft to maintain balance despite tilting.
Hope you all understand the video, and thank you for listening.